Hello folks! This time around we want to take a look at the handling of smart pointers and the use of them in pointer-based languages to try and safeguard against some of the problems that you encounter when you've got a pointer-based language for memory allocation and deallocation. So the idea is for a pointer-based language, so for a C or a C++, something like that, smart pointers are meant to kind of bridge the gap between pointers and all the problems associated with them and references, right? The safer approach taken in a lot of languages where you don't give the programmer direct access to the memory address of something. You just provide them a means for indirectly accessing it, and you safeguard their access that way. So you protect them against wild pointers, invalid pointers, because they're not creating them, dangling pointers, right? You're making sure you don't release something as long as something can still access it. You protect against memory leaks. Make sure you auto-release things for the developer. So you're taking away some of the control from the developer, but giving safeguards. And again, the idea is if you're using one of the pointer-based languages, the developer could still use just regular old pointers if they wanted to, but this provides another option, a safeguarded option, and they are more and more widely used in, say, C++, for instance. So typically in a language that supports classes, that's going to be the way they're implemented. So there'll be internal data in the smart pointer that keeps track of where the thing is actually allocated, where the resource that's been requested is actually allocated, and keeps track of when it's safe to access it, and keeps track of when it needs to be deallocated. So there'll be methods and operator overloading to support all of this stuff. So in terms of what it looks like from the developer point of view, right, you go through and create a smart pointer of the desired resource type. So if I have nodes in a graph that I'm dynamically allocating and deallocating, then I'm going to go through and create a smart pointer for nodes. Smart point. This thing can point at any node, and if I need 12 smart pointers to nodes, I can create 12 of them. But again, the idea is you create a smart pointer that can point at the desired resource type. When you want a new node, a new instance of the resource, you do that. You request that through that smart pointer. So for my pointer X, allocate a new node. When you want to get at the resource, when you want to get at the fields or the methods of your node, for instance, again, you do that through the smart pointer. Of course, we've got to work out syntax issues for this and implementation issues, but this is the idea. These are the kinds of things that your smart pointer is providing for you. You can assign or copy smart pointers, so pointer B or a pointer A equals pointer B, or pass them as parameters. Right, if you have a parameter that's expecting a smart pointer and you pass one to it, again, it's a copy operation, right? Using much like the copy constructors for classes and whatnot. And again, the idea is that the deallocation of the resource is automatically going to be handled by the smart pointer. So it's not something the programmer will explicitly do anymore. So obviously, the smart pointer has to be maintaining some information that lets it track when it's safe to access the item and when it needs to delete the item. It needs to maintain an internal pointer to the actual resource, right? The user never gets direct access to the memory location of the item, but the smart pointer needs to know where it is. So you've got this internal data you have to keep track of. So it's got that internal pointer to the actual resource. What we'll consider here is the idea that if there's a bunch of administrative information that needs to be tracked for that allocated item, for that node, for instance, then we'll allocate a sort of administrative object to take care of that information tracking. So your smart pointer might have two pointers in it, one to the node, for instance, and one to the administration data for that node. And what's going to happen is that admin object gets allocated when you first allocate the node, when you first allocate whatever the resource is. And inside it, it might do something like maintain a reference count, keeping track of how many smart pointers are referring to that node at any given point in time. So in the beginning, it's obviously just going to be one, right? Just this one smart pointer that created the node is the one that's got a pointer to it, so the reference count is one. But when you start doing things like copy pointer B to pointer A, then you're increasing the number of things that point at that. So part of that assignment operation would be updating the reference count for that node that you're pointing to. And for that matter, if you said pointer B equals pointer A used to point at something else, so we've got to decrement the reference count for that thing. So we've got all this data that's being maintained in some kind of an administrative object someplace. So what happens if you do something like an assignment, as I was just saying, we go through and copy both of the pointers, right? Let's say pointer B is referring to the node, so it's got a pointer to the admin object for the node, it's got a pointer to the node itself. When we copy pointer B to pointer A gets copies of those two things. And again, it increments the reference count for the thing B is pointing at, and decrements the count for the thing A used to be pointing at. Similar idea for passing parameters, right? If you pass B as a parameter, the reference count, since if we're assuming pass by value, the reference count for the thing that B points to is going to go up. And when the function call ends, it's going to go back down, right? When the parameter can no longer refer to it. So if smart pointers go out of scope, right? If you have a smart pointer that's local to a function or local to a loop, when that loop ends or when that function ends, again, it's going out of scope. The reference count needs to drop by 1. You're effectively destroying that smart pointer. So the reference count for the item it was referring to goes down. If that reference count ever hits 0, that's the point when you can go, nobody can get at it anymore. This is the time to delete that actual resource, to delete the node. So we've got this automated process for keeping track of how many smart pointers can get at this thing at any given point in time. When we get rid of that last one, right, and whatever operation gets rid of that last reference count, we say, okay, I've got to go destroy that object now. And that'll be part of the operation, right? And the internal pointer to that item is going to get set to null as well. So what's going to happen whenever you're carrying out these operations, and whenever a smart pointer is created or destroyed, you're updating reference counts and seeing if you need to destroy an item. Whenever you're copying things or passing them as parameters, reference counts are being updated. Right? So all of this needs to be taking place as parts of the other operations. And then in your access operations, if you try and get at a field of the node, or you try and get at a method for the node, for instance, then those operations have to involve a check with the admin object, right? These are going through the smart pointer. So it has to involve a check with that admin object to say, okay, does this object still exist? If so, please give me that method or that field. So when the programmer is using something like this, it's going to look in their code as if they're directly using methods for the item that they're referring to. But behind the scenes, there's going to be this layer of indirection where this operation involves, okay, go off, check with the admin object, and if it's okay, then return then either execute the method or return the field that they're trying to access. So you've got this extra layer of overhead in terms of the memory space that's being used for these admin objects and these secondary pointers, and you've got the extra runtime taking place, because every time you do an operation through a smart pointer, you've got these extra checks and updates taking place. Now, in terms of the safeguards that this gives you, again, the idea is the programmer no longer controls the actual dumb pointers, if you like. The programmer's never dealing with memory addresses. They can't create wild pointers or invalid pointers because they never get the opportunity to. Right? Once you've debugged your smart pointer class, then everything should be safe from that perspective. Dangling pointers are no longer a problem, because as long as there is still a smart pointer that can get at that item, it's kept alive. Right? It's never deleted until the last smart pointer points away from it. So as long as anything can still get at it, we're keeping that resource alive, so you don't have dangling pointers. Memory leaks aren't an issue, because the instant that last smart pointer goes away, we deallocate the resource. So you've gotten rid of the core pointer problems that most programmers encounter at the extra overhead cost that we've got here. So what we'll do in the next video is we'll take a look at the actual C++ version of smart pointers.